we can start this new theory lecture by young researcher. This time we are glad to have Andrea Antinucci from the CISA, which will talk us about holographic view on symmetry.
Okay,
Please.
thank you very much. Thank you for the invitation, and sorry for these technical problems. Okay, today what I will talk about are some aspects of this field, which is like exploding in recent years, the field of generalized symmetries, and I would like to introduce several concepts from the very basic, because the point is the following: that in recent years, many people discovered this new type of symmetry, and they have been used to like extracting things from quantum field theory, phases of quantum field theory. They provide new analytical tools, and this resulted in a sort of explosion of the field. There are many people from many different contexts, like string theory, phenomenology, condensed matter, statistical mechanics, who want to like apply these tools to their fields. This morning I attended a talk here in CISA from a statistical mechanical person who was talking about application of non-invertible symmetry to statistical mechanics. So there are many. This is a field which is pervading many other areas, and so there are many people interested in this business. But sometimes I feel that it's kind of hard for people from outside to enter in the field, because we are using a language of quantum field theory which is a bit different from the language which is usually like explained in textbooks. And so there is kind of a gap of language, and the purpose of this lecture is kind of to fill this gap. And so what I will do in the first part is to introduce the concept from a very bottom-up point of view. First part I will call it higher form symmetry for pedestrians, because I will try to like motivate the introduction of generalized symmetry really from the kind of perspective that you usually take in textbook, in which you present your quantum field theory with a path integral and symmetries. I will define symmetries in this first part just as transformation on the fields in the path integral. And the motivation in the first part is to show that actually even higher form symmetries can be presented precisely in the same way as transformation on fields in the path integral, without postulating an abstract action on line operators and the existence of topological operators, which for people outside the field might be a bit abstract. In the second part, on the other hand, I will introduce a modern tool which is called the Symmetry TFT, which is an holographic tool to analyze this symmetry, and it's a bit more like user friendly than other tools which were used in the past. So okay, let me start. And so
okay, sorry if I interrupt. Sorry. Yes. Before you start, since you mentioned that you have two main parts of your lecture, if you want, we can take a break in between. Just
well, I think that the first part will be way longer than the second. So let's see. Let's see at what time I finish. If I mean, okay, if I don't finish too late the first part, if it's a good moment, we can take a break. Let's see. Okay. It might be a good idea. Let's see how it's going. Okay. So okay, please feel free to interrupt me at any time if something is not clear, if you have comment, question, whatever. So, okay. The first very important thing is that my definition of what is a symmetry is the following. Usually you present your quantum field theory with a path integral. You compute correlation function with some path integral, and you insert operators. These operators can be local, can be non-local, can be like extended operator, whatever. But okay, a symmetry will be a certain transformation on the field. Let's say you have a group symmetry and your field transforming some representation, which I'm calling R, such that the action and the measure are both invariant. This is what is a symmetry. But I think I'm disconnected now. No. Okay, it's fine. Okay.
We see the screen.
Okay. This is what for me will be a symmetry, but this is not enough to say that it's a global symmetry, because it might be that all good operators of your theory don't transform under the symmetry. So what a global symmetry is such that there is at least one operator which have a non-trivial transformation under the symmetry. So a trivial example, if you have like a real scalar, it will obviously have a Z2 symmetry. It will transform under like phi into minus phi. But let me consider two more complicated examples. The first one, let's take QED. Just to clarify, what do I mean? So the action is you have the gauge field, the magnetic term for the gauge field. I'm considering scalar QED. And so the term with the scalar will have something like this. Phi, let's say modulo square. Okay. So obviously this action has a gauge invariance. Everybody knows this very well. And this gauge invariance, of course, is not a global symmetry because nothing is charged. No good operator, no gauge invariant operator, by definition, is charged. You can try to take the constant part of the gauge transformation. Let's say that you take theta to be constant, so A does not transform. This seems to be a global symmetry in the sense that the parameter is constant, but it's not a global symmetry because the only gauge invariant operator that you can construct are something like phi dagger phi, and those are uncharged under the symmetry. This is a completely trivial example, but let me consider a more subtle one. The reason why I'm making this comment is that the only point in which higher form symmetry can be subtler than zero form symmetries, it is kind of easy if you're not familiar with this concept to confuse higher form symmetries with gauge symmetries. So these two concepts must be separated very well. And actually, in the literature, there have been several confusion about it. So even like experts in the field can make mistake if you are not completely comfortable with these concepts. So the more complicated example that I want to consider is QED, even also scalar QED, but with NF flavors of scalars. Okay, so it's the same theory as before, but with the NF flavors. So naively, you might think that there is an SUNF global symmetry acting this way, just from phi I to phi I prime with a certain matrix, and this matrix belongs to SUNF. But if you think about it for a while, you will realize that the only good gauge invariant operator that you can construct are like bilinear in the scalar. OIJ is phi I dagger by J. These are invariant under the gauge transformations. But then you will realize that if you take a matrix M, which belongs to the center of SUNF, then these operators are uncharged. So actually, the center, the NF of SUNF, is not acting faithfully. So this is not a global symmetry. This is a gauge symmetry. This is gauged. And so the actual global symmetry is the quotient. It's called P SUNF. Okay, so this is very easy. And okay, the modern way to phrase this idea of performing a transformation in the path integral is by means of what are nowadays called topological operators. This is just a rephrasing, and let me explain in the following way. You learn very well from textbooks that if you have a global symmetry, let's say a continuous global symmetry, you can perform a transformation in the path integral where the parameter is taken to be not constant. This is the standard way in which you prove word identity. For instance, you have a U1 symmetry, and then you take phi going to E alpha phi. But if alpha is not constant, then the action will not be invariant, and you will take a term which is alpha d star j. This is the way to prove the word first the Noether theorem, and then if you do it in the path integral, you will prove the word identities, which takes this for d star j you look for insertion of local operators. You have the there with delta functions. Okay, very good. Now, this is where typically standard textbooks stop, but you can continue. Sorry, this is valid in X, of course. T star J in X. What you can do is to integrate X in a region, we call it D, and the boundary of this region will be a codimension 1 surface. And so if you do this integration, since this is the first term is exact, you will get a boundary term, and the boundary term is what is called the charge operator. This is the integral for this region. Notice that J, as I define it here, is a 1,4. So star J is a D minus 1,4. And you can integrate it over a D minus 1 submanifold. And so when you do this integration on both sides, on the right-hand side, you will get the sum of the charges inside the region. The sum of the charges which are linked, I mean, of the operators which are linked with this codimension 1 surface. So you get sum of the over E, let's say inside the surface. Yeah, you get this. Okay. There is a further step that you can do, which is to exponentiate the charge, and you will construct the finite symmetry action. This is just the exponential, and this will implement the finite symmetry transformation. It will make sense even for discrete symmetries. Okay, so very good. This is just a rephrasing of standard word identities, but it has some advantage. And the advantage is the following. Okay, when you said that you perform a global transformation in the path integral and I transform all the fields, this just means that from these word identities, you can notice that the insertion of the operator, if I start deforming the support of the operator, will not make anything unless when I deform it, I will cross some charge operator. So this means that this operator is called a topological operator. Okay. So what I can do is to nucleate this operator from a point. If I take it, the support to be very small, the operator will be essentially 1. I nucleate it from a point. I will expand my operator until I cross all the possible insertions. And then, if I'm like in a compact space, okay, I'm on a sphere, otherwise I have to discuss issues related with spontaneous symmetry breaking, but let's say I'm on a sphere, then I can reannihilate the operator at infinity. And so this is what it means performing a transformation over all the fields. But this topological operator makes something more, because it allows me to implement the symmetry just locally. Gives me is equivalent to say that I have a current. So for instance, if I have a continuous symmetry, it is enough to discuss currents. But if I have discrete symmetries, this is saying something more. So it is a rephrasing, but already it's kind of useful. But now let me go to the actual interesting part, which is related with higher form symmetries. And I want to define higher form symmetries precisely as I defined this kind of ordinary symmetries, which I will call these are called zero form symmetries. The reason why I called zero form, zero refers to the fact that the charged operator are local operators. And the topological operator associated with zero form symmetry is always of codimension 1. Now, I want to define higher form symmetries in the same way. So let me consider an example, which is Maxwell theory. So just a theory of free photon. Very good. So now it is very important not to confuse higher form symmetries with gauge symmetries, which are not symmetries, are just redundancy of the path integral. And to understand why higher form symmetries exist in this theory, you have to keep in mind what does it mean performing the path integral of a gauge field? The gauge field is described by some kind of gauge bundle over your manifold. So you have a gauge bundle of this sort, and you have to sum over all gauge bundles and over all connection on it. I will clarify in a moment what do I mean, but I will explain higher from symmetries in Maxwell theory in two different ways. The first one is a bit more pedestrian. The second one is a bit more precise. It will be the one which can be generalized to non-abelian gauge theory. But for the moment, let me just say that I'm summing over connections, connection A, and F is just the A. And so the action is invariant if I shift my connection by a sort of closed form. Let's see, d lambda is equal to 0. Okay. And the simplest possibility are, of course, gauge transformation, where I take my closed form to be exact. And okay, this is a gauge transformation because there is no operator which is charged under this symmetry. The operator are F polynomials in F and the Wilson line operators. Wilson lines, which will be very important in this discussion. Okay? Everything is not charged under this. But now, if instead I take A going to A plus lambda, where lambda is closed, but not exact, then F, of course, is invariant, but the Wilson line is not. The Wilson line will transform by a phase, which is the integral of lambda over this curve. Okay? So in general, this is a global symmetry. There is no local operator which is charged under this symmetry, but there are line operators which are charged under it. So this is what is called the one-form symmetry. Okay? And here one refers to the fact that the charged operator are lines. But now you have to be very careful, and there are subtleties about this discussion. First of all, I have not discussed large gauge transformations. And at this point, you have to decide whether to include large gauge transformation or not. So here you have possibilities, and the possibilities are in one-to-one correspondence with the choice of what is the spectrum of your line operators. So something that you may want to do is to not include large gauge transformation. So you perform your path integrally and you don't mod out by large gauge transformation. And this means that all Wilson line operators with any real value of k, here k can be any real value, are good operators. And so the one-form symmetry is a very large group. It's a non-compact group. It's basically R. Because for any value of the holonomy of lambda, the integral of lambda on a curve, there will be at least one operator which is charged. But this means basically that the gauge group of this theory is not U1. The gauge group is R. So this is not U1 Maxwell, it's R Maxwell. So this theory, for instance, does not include monopoles. In this theory, the integral of f over 2 pi over any sphere is always 0. And so, for instance, this theory cannot come from the Higgsing of an SU2 gauge group into U1 because there are no monopoles. This cannot be the low energy, or let's say the Georgi-Glashow model. If you want to include monopoles, you want to consider the gauge group, this gauge. If you want to consider the gauge group to be U1, then you have to include large gauge transformation. So this means that you have to mod out by transformation of this sort if the integral of lambda over 2 pi on any curve is an integer. So these are not global symmetries. I'm declaring that these are gauge symmetries, these are gauge invariances. And therefore, my good operators must be invariant under this transformation. And so, for instance, the Wilson lines with k, which is not integer, are not allowed. Okay? Now, my good operator will be only the Wilson line with k, which is an integer. And so therefore, if you come back from the previous discussion, you will notice that the value of the holonomy of lambda, which are acting faithfully, are only those. Okay, this was like, let me call it in a different way. Let's not me call it lambda, but like psi. Now you perform I going a to the psi. This was the gauge transformation. Now a global transformation is such that this belongs to the interval 0, 1. Okay, and therefore the one from symmetry becomes compact, becomes R over Z, which is what is also called U1. Okay, so this is a different global structure of the same theory. This is a general message that will be important in the following, that the choice of the global structure of the gauge group, if you fix the algebra and you want to make a choice of the global structure, this is in one-to-one correspondence with the choice of the spectrum of your line operators. If you restrict your line operators, then you are enlarging your gauge group and you are reducing the one from symmetry. Okay, very good. And okay, but now you may have a general question, which is, okay, in the case of continuous zero from symmetry, we have a current and we have worded entities. Do we have a current and worded entities for higher from symmetry? Current. And actually, what you can do is the following. You do the usual trick of performing a global transformation by making the parameter not global, but local in the path integral. And so the action will be not invariant, and you will derive ordered entities. But here, the parameter is this psi, which is already not a constant, it's a one form. But so the analogous thing of taking it not a constant is that you perform the transformation with psi not closed. Okay? So if you do it, basically you will realize that even f will not be invariant. So f will go in f plus big psi, of course. And so the action will change by something like this. Integral of d psi, wedge star f. Then you integrate by parts. This is precisely the same thing that you get with zero from symmetries when you try to prove the Noether theorem and the worded entities. So here you realized that you have a current. You actually have a current, which is star f. I mean, okay, in this language the current is really f. So the current now is not a one form, but it's a two form, right? So you can try to play the same game as always. You do this change of variable in the path integral, and you will get worded entities. But the worded entities, since the all operators which are charged under this symmetry are lines, will be non-trivial only if you have insertion of Wilson lines. If you only have local operators, this worded entity will be just empty. Good. But then, as I told you before, with a current, we can construct a topological operator, and we can do the same here. The only difference is that the topological operator will not be of codimension 1, because I have to integrate star f, and star f is a d minus 2 form. So the topological operator will be of codimension 2. Is the integral of star f on a codimension 2 surface, right? So, and this fact make perfectly sense, because if you now want to perform a transformation globally in the path integral, as I told you, you have to nucleate this operator from one point, enlarging it, and annihilate it at infinity. But it cannot be of codimension 1, because if it is of codimension 1, then you will cross some local operator. But as I told you, local operators are all invariant under this symmetry. local operator cannot transform under this kind of symmetry. Only line operators can transform. But if this topological operator is of codimension 2, the local operator, when I enlarge this, I can always avoid local operators. Imagine that if you are in 2 dimensions, so a codimension 2 object is like a line. So if I nucleate a line from one point and I try to annihilate at infinity, I can always avoid crossing local operators. But I cannot avoid crossing line operators. So this is perfectly good. And so the general lesson that will emerge is that P-form symmetries will act on p-dimensional operator and will be generated by d minus p minus 1 dimensional topological operator. But in the way I'm presenting it, this is a consequence. The way I'm presenting it is that you start from some transformation on the fields on your action, and then you derive this. The only difference is that the basic transformation that you do are on non-gauge invariant degrees of freedom, and the first non-trivial operator they can construct are extended operators. But apart from this, it's exactly the same thing that you do with normal symmetries. Now, I want to arrive at explaining how the symmetries can be defined even in non-abelian gauge theories. But to do this, I have to present what I did for Maxwell theory in a slightly different way. So, are there questions? Okay, good. So, let me present the higher form symmetry, the one from symmetry of Maxwell theory in a slightly different way, which is more precise, but allows me to generalize. The basic slogan is that actually you have to be careful because the connection is not really a one form, it's a locally defined one form. And if you understand better what is the structure, the gauge bundle, you can always, by some gauge transformation, trade the action on the one form by an action on the transition function of your bundle. So let me explain what do I mean. First of all, you decompose your manifold, you patch it, so you decompose it in open sets, and the gauge bundle is defined basically by transition function from the double intersections to the group here. Okay, and these are required to satisfy the cocycle condition on triple intersection. So on Uijk, the triple intersection of three open sets, you must satisfy G I, Jk, Gki equal to 1. Okay, this is called the cocycle condition. So very good. And a connection on this gauge bundle is defined by a family of local one forms. So this is a local one form. Ui varied in G with some gluing property on the double intersections. They must glue in this way using the transition functions. And importantly, the question that I wrote must not be confused with a gauge transformation. This is just a defining condition for the field. A gauge transformation is, on the other hand, defined by a family of functions Ti from the open set to G, acting both on the connection and on the transition function in the following way. on AI is formally the same as above. And this is the usual formula for gauge transformation, but it also acts on the transition function, essentially by conjugation on the sides. And the second equation, which you are probably less familiar with, is required to be compatible with this gluing property that I wrote above. Okay. Very good. Let us specialize to the case of U1, so that I can explain how higher form symmetries are presented in this language, and then we will come back to the non-abelian case. So in the U1 case, of course, you can write something like this. This is written in terms of phases, and therefore the gluing condition will be AJ equal to AI plus T. This is gluing. Now, a gauge transformation, so it's again very similar. If you specialize it to this case, a gauge transformation will be the standard form that you know in abelian gauge theory, but then we have to act also on the transition function that now are defined by this phases theta. Now let me go to the higher form symmetries. Well, before I told you that the higher form symmetry is a transformation of this kind, A going to A plus lambda, where lambda is closed. It's closed but not exact, but as you know very well, any exact form locally, any closed form locally is exact. So the restriction to any open set can be written in this way. But then you may notice the following: then if I take this gauge transformation that I wrote, I can perform in any patch a gauge transformation with phi I equal to minus rho I, and I will reabsorb my area from symmetry transformation. But the price that I pay is that now, so I'm doing at the same time this shift of A by a closed form and this gauge transformation to reabsorb it. So A will stay invariant under the one from symmetry transformation, but the transition function will change. It will change by multiplication of this eta, which I'm defining in this way. Rho J minus rho. Sorry. And by construction, this eta will by itself satisfy the ecocycle condition. And this is good because the new transition function will satisfy again the ecocycle condition. So mathematically, eta is what is called a check one cocycle. This is denoted in this way. This is not very important at this point, but let's see if you find this terminology somewhere. Okay, so now what we did is, by understanding better what is a gauge bundle and performing a local gauge transformation, we were able to trade one from symmetry transformation as an action on the connection by an action on the transition function which doesn't act on the connection. And now you might be confused by something, because as I told you before, the one from symmetry transformation acts in the Wilson loop, which is written in this way. So you may ask, well, but if A is not invariant, how is it possible that this one from symmetry transformation does something on the Wilson loop? It seems that now even the Wilson loop is invariant. And this is kind of an important lesson that you can learn from this story, that is not usually spelled out, that this is the wrong definition of the Wilson loop. It's wrong. Okay. This is wrong if you present your gauge bundle correctly, because when you take your first differential geometry class, I guess that your professor taught you how to integrate one forms over curves. not connections. Connections are not one forms. Connections are locally defined one forms. So if you want to integrate a connection over a curve, you have to be much more careful. And so you can do it locally, patch by patch. So in each patch, so you basically you divide your curve gamma in arcs, and each arc is lying exactly in one patch. Okay, so that on each arc, A is really a one form. And so what you can write is the following: you integrate A on the first arc, but then when you go to the second one, you have to insert a transition function, and you continue this way. Until you close it. Okay. So this now explains the puzzle, because A is invariant, but I'm acting on the transition function, and indeed you will realize that when you perform this transformation that I explained, you precisely get the same factor I explained you. So you get something like here I get K. So the Wilson line, even defined more precisely in this way, will get this kind of factor. Okay, very good. So now we are able to generalize to non-abelian gauge theories. So now I will take G to be non-abelian, and indeed it's always the case that people trying to enter in this field are confused by why non-abelian gauge theory are said to have a center symmetry. Because in the original paper, in the generalized global symmetry paper, there is a very confusing statement. They say that non-abelian gauge theory has a one-form symmetry because the connection can be shifted by a one-form valued in the center, which I don't really know what does it mean, and many people are confused by this. I think that what they mean is really what I'm going to present, which is basically what I did in the abelian case applied to the non-abelian situation. And this allows also other generalization, even including matter fields and so on. And I think it's a point that should be kept in mind when you work with this stuff, because sometimes if you are not really comfortable in why this theory has a center symmetry, you might find mistakes. So okay, the presentation now is precisely the same as I did for the second time in Maxwell theory. So this the eigenform symmetry will not act on A. So A, the connection, is invariant, but the transition function will change. Let's say in general, by a certain element, this will be a function from the double intersection new group in general. Then we will see how do we get the restriction. So now A is perfectly invariant. We are changing the transition function, but now you have to be careful, because when you perform this transformation, you should still satisfy the ecocycle condition. And now the ecocycle condition is slightly modified, because you have this jk eta jk gki ki equal to 1. And so it is not enough to require that the eta itself satisfy the ecocycle condition, because you should be able to commute eta with G. And so in order to do this, you have to require two conditions. The first condition is that the eta ij are valued in the center of the group. And the second condition, so this for sure immediately gives you a restriction, because the center in non-abelian gauge theory is a discrete group. So if you have function from double intersection to a discrete group, this function must be constant. So this eta ij is a specific value for each pair of ij, defining a double intersection, and moreover, this satisfies the ecocycle condition. Okay. And now the cohomology group that you get is much simpler than the check cohomology group I was explaining that basically nobody is ever talking about, because this is just, let's say, ordinary singular cohomology. It's like cohomology valid in the center. You don't have to discuss these complicated things because the eta ij, for this reason, is constant. So okay, and if you repeat the same procedure I told you before for the Wilson loop, again you will get that the Wilson loop will change. If you take a Wilson loop in a certain representation R, and you act with a central element Z, the one from the one from symmetry transformation given by Z, you will get that the action is the evaluation of the Z in this representation. Okay, so you conclude that the one from Z, yes.
Sorry, I have a question.
Yeah.
But does the second condition need to hold all the time? Because if the second condition holds all the time, then I guess that I need the first one for sure.
So, sorry,
do I need the?
Can you repeat that? Why do we need the second condition?
Yes, sorry. Let me move where I can speak. Sorry. The second condition, sorry, do you need perhaps necessarily the second condition or not?
Yes, you need it because of the first condition.
Like you need it for I don't know. Is the usual gluing condition. You require gluing condition to the eta, and then this requires you to ask for eta to commute with everything else, or I don't know what's the order.
Okay, the important point is the following: the transition function must satisfy the cocycle condition. Okay. The G. Then you are performing this transformation on the G. You are sending G to G prime, which is G eta. Then this new G prime must satisfy the cocycle condition. So this equation that I wrote here is basically the cocycle condition for the G prime.
Okay.
The G are satisfying the cocycle condition. So there is no hope for this to hold if eta is not commuting with the G.
Okay.
So this requires the first condition. Then you commute the eta, and since the G are satisfying the cocycle condition, you get the second condition.
Okay. Thank you. Yes. Thank you very much. Thank you very much.
So okay, what we found here is that for non-abelian symmetries, for non-abelian gauge groups, the one from symmetry is given by the center. So the only conserved number, let's say for SUN, is the anality. So this is basically a precise and rigorous way to prove the standard folk statement that, let's say, in Yang-Mills theory, the gluon number is not conserved, but only the gluon number mod n is conserved. So this is really the precise way of proving it, because here, essentially, you are saying that Wilson lines, the only real quantum number of the Wilson line, differently from what happened in abelian gauge theory, is not really the representation, but is the anality of the representation. It's class in the center. Let's say for SUN is the anality, but for other group it's just okay. It's representation in the center. So very good. Now before going on, and this will be important in the second part. I have to introduce another class of higher from symmetries which exist in gauge theories, which are magnetic symmetries. Okay, no, nobody asked me, but here I actually presented in a precise way how the higher from symmetry acts on the field, but I haven't told you what are the topological operator implementing the symmetry. That are much more complicated to introduce. It is possible to define them. I will not do it. These are called Gukov-Witten operator, are co-dimension 2 operator, which have been introduced by Gukov and Witten. in the context of supersymmetric theories, but you can introduce it even in Young-Mills theory. These are a bit more complicated to define, but in any case, you can define a topological operator implementing this action. But I think it's more clear, instead of postulating the existence of this operator, to discuss the symmetry really as a transformation on the degrees of freedom that you have in your fact integral. For magnetic symmetry, it is kind of the opposite. For magnetic symmetry, is much more easy to show you that there is a topological operator implementing the symmetry, and sometimes it's a bit more tricky to define what are the charged objects. Fortunately, for the case of U1, both things are easy. So I can define both the topological operator and the charged object. And indeed, as I told you before, when the gauge group is U1 and not R, the theory has monopoles. The rest are not dynamical monopoles. If you have a UB completion, like in a certain non-abelian gauge theory, you have breaking from SU2 to U1, you will have dynamical monopoles. But in the strict IR, this will be infinitely massive, and they will correspond to certain operators. And these operators are defined as disorder operator by prescribing that you have a point. Sorry, in general, not a point. In general, you will have a D minus 3, D minus 3 manifold. Let me call it, say, gamma. So this D minus 3 manifold will link with a certain surface, and you prescribe that the first Chern class of your bundle on this surface is given by a certain number, C. And this will define what is called a 't Hooft operator with charge n. And it will be supported on this gamma. This sphere, this S2 sphere, is a very small sphere linking with gamma. So in 3D, this gamma is a point. This will define the famous monopole operator. In 4D, it's a 't Hooft line, and then in higher D, you will grow. Okay, these are the charged objects of a certain symmetry for which it's very easy to define what are the topological operators. Indeed, in Maxwell theory, we discussed before this conservation law, but there is another obvious conservation law, which is just Bianchi identity. So on top of the two-form current, which is F, you also have a D minus 2 form current, which is star F, which is associated to the second conservation law, 1, 2, which is the Bianchi identity. And this allows us to construct a codimension D minus 2, namely a dimension 2 operator, supported on a surface, which turns out to be topological. So you just integrate F. So notice that this is precisely, I mean, in a certain normalization, this is this equation that I wrote here, in the sense that this operator is measuring the magnetic flux. And this topological operator, so is of codimension D minus 2, which can be written as D minus 1 minus 1. Sorry. Yes, this is, of course, this equation is true, but no, sorry, is of codimension 2. Yes, sorry. Of codimension D minus 2 is of dimension 2. So the charged object will be, as I told you, of dimension D minus 3, because something of dimension D minus 3 can link with something of dimension 2. The dimension must add up to D minus 1. And so these charged objects are these 't Hooft operators. So this is the story in Maxwell theory. In non-abelian gauge theory, the situation is slightly more complicated, but not that much. Of course, in Maxwell theory, you don't have the Bianchi identity as simple as here, but you want to construct a two-dimensional topological operator, and you cannot do it for groups like SUN. For SUN, you cannot do it. For SUN, there is no magnetic symmetry. In order to have a magnetic symmetry, you need to have a certain group which is not simply connected, so by one different from zero. And indeed, in this case, there is a certain characteristic class of G bundles, which is called W2. some point in the literature, people started to call it Stiefel-Whitney class, but this is I learned that this is not correct. There is actually no university accepted name. Maybe somebody is calling Brouwer class. It is not well studied by mathematicians. Mathematicians are only interested in this case, the case in which G is an orthogonal group. So in that case, it's correct to call it Stiefel-Whitney, but in general, you can just call it a degree two characteristic class of G bundles. And so since this is a characteristic class, you can construct a topological operator. You can construct a topological operator in this way. You take a certain representation chi of pi1. The symbol means that this is the group of functions from pi1 to u1, which are characters. So these are just representation of the fundamental group. And so what you do is to construct this symmetry operator. U of chi is labeled by this representation. So you evaluate the exponential of the integral of this characteristic class in this representation. So basically, what we are getting is that non-abelian gauge theories have magnetic symmetries, which are given by the pi1. Okay. This group of representation for discrete groups is always isomorphic. To groups. So this is the same. And this symmetry is always a d-3 form symmetry. Okay. So the conclusion is that for non-abelian gauge theories, which will be basically the subject that we will study from here to almost the end, non-abelian gauge theories have a one-form symmetry given by the center, and a d-3 form symmetry given by the pi1. Okay. Now, it is often the case that you can go from one to the other. Let me explain what do I mean by this. First of all, just to give an example, four-dimensional SUN Young-Mills, we'll have the first time, let's call it 1 and 2. We'll have the electric symmetry will be Zn, and there is no magnetic symmetry. While if you take PSUN, which is SUN divided by Zn, so you are modding out the center. So there's a both one form in this case, because 4 minus 3 is 1. So now PSUN has no center, but it has a pi1, which is Zn. So you see that we are exchanging the two. And indeed, you can often go to one global form of the gauge group to the other by just gauging the one form symmetry. And the reason is the following. There is a very old and classic argument that if you have a p form symmetry, in the dimension, let me call it gamma, and you gauge it, so to gauge it, you have to introduce a gauge field for gamma, and a gauge field. So for zero form symmetry, a gauge field is a one form. For one form symmetry, a gauge field is a two form, and so on. In general, it will be a p plus one form of the manifold valued in gamma. If you gauge it, you will get a theory with a dual or quantum symmetry, which is of degree d minus p minus 2, and the group is again this group of characters. Okay, and the reason is the following. As I told you, to gauge the symmetry, you have to introduce this gauge field, which is a p+1 form. So what you can do is to construct the following topological operators in the gauge theory, labeled by these characters, and these are supported on a p+1 dimensional manifold, and are the evaluation of this. So you have this additional gauge field, and you can construct holonomies for these gauge fields. But since this gauge field is discrete, this is a topological operator. And so this is labeled by the characters of the one from symmetry group that you're gauging. And so you will notice that the degree is d minus p minus 2. And so applied to the case of non-abelian gauge theories, you start from a one form symmetry in the dimension. So you have the center symmetry. Let's say you start from a simply connected group. So it has a center symmetry, but no magnetic symmetry because the pi1 is trivial. You gauge it, and you get a d minus 1 minus 2, which is d minus 3, form symmetry, which is ZG, the G check, the group of characters of the center. And it turns out that for a simply connected group, this is equal to the pi1 of the group given by G divided by the center. So this is what I told you, for instance, in the example of SUN and PSUN. So you might suspect that starting from an SUN gauge theory and gauging the center one form symmetry, you will get the PSUN theory. This is indeed what happened. And so the SUN theory and the PSUN theory are said to be different global variants of the same theory. Let's say they have identical local dynamics, but different global structure. And for instance, the partition function on a general manifold for SUN or PSUN will be different, but more importantly, the spectrum of line operators will be different. So for instance, one form electric symmetry, the one associated to the center, can be used to characterize precisely what is confinement in gauge theory. Confinement in gauge theory can be defined as the fact that the one form symmetry, the one form electric symmetry, is not spontaneously broken. And so the Wilson lines, as you know, are order parameter for confinement. If the web of the Wilson line is 0, since the Wilson line is charged under the one form symmetry, the one form symmetry is preserved. While if the Wilson line has perimeter law, the perimeter can always be reabsorbed by a counter term on the line, and the web of the Wilson line will be a constant, and the one form symmetry will be spontaneously broken. But the opposite happened for PSUN. For PSUN, you don't have Wilson lines, you have Tooth lines, and so the criterion for confinement is not the spontaneous break. You don't have the electric symmetry, so you will look for the new order parameter will be the Tooth lines, and the theory will be confining if the Tooth line has perimeter law. So this is the old idea of Toft that confinement is associated to the condensation of magnetic monopoles. So okay, very good. In going from SUN to PSUN, to going from a simply connected group to a non-simply connected one in 4 dimension, you can do also a slightly different thing. Let me do it in the case of SUN. So as I told you, to do this, you have to introduce a gauge field. Let me change a bit the notation. Let me call it B. So this gauge field is let's say we are in 4 dimension here. So you want to gauge this one form symmetry, and when you're gauging it, You can also modify your action by adding this kind of term, which is roughly speaking 2 pi r over n integral on your manifold of b square. So b is a 2 form, you take the square is a 4 form, you can integrate over the manifold, and this is a discrete torsion. And so what you will produce is not really the PSUN theory, but a slightly different version of the PSUN theory, which is called PSUN R. This R will take value from 0 to n minus 1. And this parameter in the PSUN theory will play the role of a discrete theta angle. So now, basically, the theta angle in PSUN is no longer 2 pi periodic, but it's 2 pi n periodic. And going to, you can have different intervals which are labeled by this number R. So you really have n version of the PSUN theory. Like in SU2, you have in total 3 versions. You have SU2, then you have SO3, and you have another version of SO3 where you are turning on this discrete angle. And all of these are different global variant of the same theory with gauge algebra SU2. Okay, so before going on, and I will in a moment I will go to the second part, but I just want to make a comment that it is not always guaranteed that you can gauge an higher form symmetry. Higher form symmetries, as all symmetries, can have 't Hooft anomalies. And 't Hooft anomalies are obstruction to gauging the symmetry. And the way to detect 't Hooft anomalies is that you couple your theory T to a background field for the higher form symmetry, and you perform a gauge transformation. It can be that the partition function is not invariant under the gauge transformation, but you pick a phase. Then you're always free to add local counter terms to your action to try to cancel this phase. But if you cannot do it, you will declare that your symmetry is a 't Hooft anomaly. And also for higher form symmetry, the 't Hooft anomaly must be matched along the RT flow, and this gives you constraint for the higher phases of your theory. And an important point on anomalies that as for higher form symmetries, as for zero form symmetry, they cannot be cancelled by local counter term. If you really have an anomaly, it's something that you cannot cancel by a local counter term in the dimension, but it can be cancelled by a topological action in one dimension higher, which is called inflow action. It's a classical action of your background field, and your system plus this topological action in one dimension higher is anomaly free. And a way to interpret this inflow action is that in one dimension higher, you have a certain topological quantum field theory, which is trivial. It has an Hilbert space which is one dimensional on any manifold. The partition function on closed manifold is 1, so it has only one state. But even if it is trivial, this theory has symmetry, has the higher form symmetry, and this action is basically the response of the theory to couple the theory to a background field. So this point of view will be important in the second part, in which I will introduce the modern tool to analyze symmetries, because it is essentially a generalization of this idea of cancelling anomalies by inflow. Now, I'm slightly approaching the second part, and now what I will want to talk about is briefly the general framework that we are trying to understand, which is the framework that are called of global categorical symmetries. So what I showed you is that to any symmetry defined as a transformation of the fields in the path integral, you can associate a certain topological operator. And this explains, for instance, why we like so much symmetries, why they are so useful to constrain the infrared behavior of quantum field theory. And the point is really that you start from some UV description, you study the symmetry of your problem, and then since the symmetries are associated to topological operator, when you flow along, you go to very low energy, which means going to very large distances. Since these operators are topological, they cannot change with the scale, and they will keep existing at all energy scales. So symmetries and their anomaly must be matched along the energy flow, and this is beautifully explained by this identification of symmetries with topological operator. But then you have to ask, why don't we consider more general topological operator than those associated with transformation on field of the action? And it turns out that these more general symmetries, which you might be more comfortable to call them non-symmetries, because these are topological operators which are not associated with any transformation in the action. These are kind of let's say violation of the Noether theorem. There are conservation laws which are not associated to any symmetry, and this kind of operator turned out to exist, and people call them non-invertible symmetries, categorical symmetries. They are just different names, and in other fields there are other names. The characterization is that you have certain topological operators supporting on some submanifold of the codimension that you want. So you can have even like non-invertible higher from symmetries or whatever, which are not associated to any kind of transformation in the fields of the path integral. And for this reason, there is no reason why they have to fuse as a group. So when you fuse two of this operator, instead of producing one other operator of this theory, you get a sum of operators. This is kind of fusion algebra, right? So this is a generalization. It's something you cannot get from something which comes from a simple transformation of the fields in the path integral. Here, this coefficient n can be numbers. If you are in 2D, they are really numbers. It turns out that if you go to higher dimension, these numbers are depending on the support of the operators. And so technically, people say that these numbers are actually partition function of topological quantum field theory living on the defect. So there is some kind of very complicated mathematical structure, and two remarkable facts that have been discovered in the last few years, let's say 2 or 3 years, are the following. The first fact is that the symmetries are very common. Are very common even like completely ordinary quantum field theory. You don't have to look for exotic theories. Let's say a list of very common QFT with this kind of weird symmetry include like the Ising CFT and many other minimal models, compact boson in two-dimensional rational radius. There are WGW models. There is 2D adjoint QCD, Chern-Simons theories, QED in 4 dimension, and many other, like n equal to 4 super Young Mills, n equal to 1 super Young Mills with non-simply connected gauge groups, Argyles-Darras theory. There are, I mean, many common theories actually share these apparently weird symmetries, which are maybe you want to call non-symmetry, that you are not associated to a transformation of fields in the path integral, but they are associated to some topological operator. And another fact, which now people are kind of convinced about, is that the structure describing the symmetry, while for ordinary symmetry, you know that is group theory, here is some more complicated and abstract mathematical topic, which is called higher category theory. So this is a very scary topic for people coming from other fields and even from people inside the field. It's even scary for mathematicians. So it's a topic which is still under development in math, and this is why many people are afraid to try to use it, because many things are not defined, nothing is clear. There are a lot of definition, and nobody knows how to do manipulation conveniently. But indeed, the main point of the last part of my lecture is to introduce a tool which have become popular in the last year or year and a half, which allows us to handle with these complicated symmetries without really caring about this complicated mathematical structure. And indeed, one of the points why we are so good in doing manipulation with ordinary symmetries is that we know very well how to couple ordinary symmetries to background. So we don't really have to deal with the symmetry in abstract sense. We can track the symmetry by coupling the symmetry to background. We can track the background along all the RG flow, computing the anomaly in the way I told you, like performing a gauge transformation of the background gauge field and so on. While for this complicated categorical symmetry, we don't really have a good notion of what is a background gauge field for these symmetries. So for this reason, it's very hard to perform manipulation with them. But fortunately, and very recently, a tool emerged, which is kind of a generalization of what is a background gauge field for this complicated symmetry. It is not completely clear at first sight that it is a generalization of this concept, but I will try to convince you that it is. And this concept is called Symmetry TFT. The extended name is Symmetry Topological Field Theory. It's a holographic tool in the sense that it's a way to encode all the information of your symmetry in a topological quantum field theory living in one dimension higher. But differently from the more standard inflow action, this topological field theory is not a trivial theory, it's really a non-trivial TQFT. So in the rest of the lecture, I will try to explain this. So let me ask if there are questions at this point, or maybe we can even do some small break if you want.
We can take a 5-minute break. I guess we can restart with the second part of the lecture. Thanks.
Okay, very good. Okay, so as I was saying, one of the reasons why it starts to be so hard to extract useful information from the existence of the symmetry, because at the end we want to extract physical information. We want to be able to say something like, okay, our theory has this non-invertible symmetry, is Categorical symmetry. What can we predict? So we should be able to extract information, something like anomalies or generalization of this. And this turns out to be very hard because it is not clear what is the right concept of a background field for this categorical symmetries. And the tool that emerged in the last year, that at the beginning I think it was not really recognized to be a tool for doing this, it is what is called this Symmetry TFT, which is kind of coupling our theory to background field, but not in the same dimension, but in one dimension either. So let me explain what do I mean by this. This is really an holographic tool in the same sense as holography. You know very well that in ADS-CFT, the statement is that let's say the partition function of a certain CFT with sources, let's say you add sources, and these are external sources, which are like sources for operators, is computed by the partition function of gravity. Partition function of gravity, where in the path integral you have certain fields, and you impose that the boundary value of these fields are fixed to be equal to the sources of the boundary theory. So basically, you can interpret this as saying that the sources of your QFT are made dynamically in the bulk. So you can try to reverse the logic, and in principle, you may hope to construct from a bottom-up perspective the gravity dual of a given quantum field theory by coupling the quantum field theory to all possible external sources you have to know all the operator of your theory, local operator, extended operator, whatever. You have to add all external sources, and then you extend your sources to the bulk, and in the bulk you make the sources dynamical. So this procedure, as far as I know, it's impossible, and I don't think that nobody ever succeeded in constructing a gravity dual in this way. But in principle, this is really what the gauge gravity duality is. What we can do is a much more modest thing, but even like still very useful, which is consider among our sources only background gauge field for discrete symmetry. So for us, the JAI will be background gauge field for finite symmetries. So what we can try to do is to take a certain quantum field theory, and we know the symmetries of the theory. So for the moment, I will talk about invertible symmetries. Then at the end, I will mention what is the generalization. But for the moment, I just want to rephrase the standard way of dealing with the ordinary symmetry in this new language, and I will explain why this new language can be generalized to non-invertible symmetries and categorical symmetries. So I take all the background gauge field for my finite symmetries. I extend this background field to a d+1 dimensional bulk, so this is a CFTD, and I extend it to a d+1 dimensional bulk. And then I make the sources dynamical. And this is something that fortunately I can do for discrete symmetries. And I want to be concrete and consider the example of let's say 4D. Let's say in young meals, but you can consider super young meals, and this will be important. The following: the all important thing is that you take 4-dimensional gauge series with one form symmetry. So think about like the example I introduced before: SUN, PSUN, and generally PSNR. Okay. So let's say that we start from SUN. What you can do is that we said that we have a one form symmetry Gn, and we couple it to a background field. Then we extend this background field in the bulk, and we gauge it. So essentially, this B in the bulk can be interpreted as the background field for a one form symmetry in the bulk. But so the bulk will be 5-dimensional. Bulk is 5-dimensional. And so if I gauge a one form symmetry, which now is acting on anything in the bulk, there is nothing charged under this. This is in principle, I just constructed like the inflow for this symmetry, because I'm just saying that the symmetry is trivially acting in the bulk. If I gauge it, I get a dual symmetry, and the dual symmetry has degree 5 minus 1 minus 2, which is 2, right? So in the bulk, I get a dual symmetry, which is a Zn. Let's say in principle is the group of character of Zn, but this is more equal to Zn, and this is a two-form symmetry. But on top of this, since our one, in principle, the original one form symmetry trivially acting on the bulk indeed was acting on anything on the bulk, when we gauge, we also get a kind of center symmetry. But since we are gauging a one form symmetry, the center symmetry will be a two form symmetry, and this is another two form symmetry. So the full two form symmetry is Gn times Gn. Okay, this is a two form symmetry of the bulk, and indeed the bulk can be described as a pure gauge theory for a one form symmetry Gn in 5 dimensions. So this is a continuum formulation. The continuum formulation is an action written in this way. It's called a BF action. So in 5 dimensions, you put two, in principle, continuous gauge field, C and B, with a kind of Chern-Simons-like action. These are both two-form gauge fields. This makes sense in 5 dimensions. So the equation of motion of C tells that dB is 0. And the equation of motion of P tells that dC is 0. And so this the full content of this theory, almost the full content of this theory, is described in terms of topological surface operators, which are like, let's say, like Wilson line of B, Wilson surface, because it's dimensional, a Wilson surface of C. And as you notice, the theory is quadratic. Is a completely trivial exercise to perform computation with this theory. You just have to integrate out things. Is a Gaussian integral, and you can compute, for instance, correlation function of this operator. Let's say you take two different supports, and you can notice that in 5 dimensions, surface can link. So you can have, like, in 3 dimensions, you can have lines, you can have loop linking in this way. In 5 dimensions, you will have surfaces linking in this way. So let's say that this is a picture in actually in 2D, but it's a representative of 3D, but it's valid in 5D. And so if the surfaces are linking, you will get a braiding, a so-called braiding phase. And from this equation, you can notice that the operator with small n equal to big N and V equal to big N are trivial. So this is why we say that this theory is a Z-n gauge theory. It's a topological field theory in which basically the only content of this theory are n operator of type U, let's say, small n. And same thing for B. And basically, this theory is characterized by this type of braiding phases. Okay, so we constructed this theory by a kind of holographic logic, just gauging the one-form symmetry of the boundary in the bulk. So we are turning on background field, we are standing in the bulk, and then we make them dynamical. Okay, but one important thing is the following: that in making B dynamical, I should have fixed boundary condition for B on the boundary, but I didn't do that. And so I'm leaving B and C to be fixed at the boundary where the original theory lives. And the consequence of this is that my boundary theory is no longer an absolute theory, but it is what is called a relative theory. It is relative to a 5-dimensional bulk. So my theory T is living on the boundary, does not exist alone, and is the boundary of a TQFT in 5 dimensions. Okay, so this is a kind of situation which is familiar if you know, like, 6-dimensional 2,0 theories describing the world volume of M5 brane in M theory. As a relative theory, they don't exist alone. They require a 7-dimensional TQFT as a bulk. In that case, it is necessary. Here we are doing a bit artificial because we started from a theory which exists by its own, but we are doing this gauging of the boundary and the bulk together. But to recover our, so this is relative. To recover our original TFT, we can put an additional boundary. So we put basically our TQFT in a slab. We put an additional boundary here where we impose topological boundary conditions. So this is a TQFT. TQFT can have topological boundary condition, namely boundary condition which, to be defined, don't require to introduce a metric on the boundary. For instance, Chern-Simons theory famously typically don't have topological boundary condition, only have conformal boundary conditions. But this kind of TQFT in 5 dimensions always have topological boundary conditions. And one boundary condition that you can impose is like B equal to 0 and C free. You can check that this is a consistent boundary condition from this action. And after you impose topological boundary condition, since the bulk is a TQFT, you can do this slab compactification, and you will get again an absolute theory T4, which it turns out that with this particular boundary condition is precisely the original theory. Let's say SUN. it's kind of intuitively why. Basically, we started from SUN Young-Mills with a one-form symmetry. We turned on this background field. We made it dynamical in the bulk, but then we are adding another boundary which freezes the dynamics of this background field. So it's kind of intuitive why at the end we get back the SUN theory. But now what we can do is to fix the bulk TQFT, fix the boundary, let's say the relative boundary, and we start changing the topological boundary condition. So another topological boundary condition that we can impose is C equal to 0 and B free. And you immediately understand that if B is free on this topological boundary after this slab compactification, you will get a theory where B, the background field for the one-form symmetry, is still dynamical. So if the background field is dynamical in the boundary, this will correspond to SUN, where we gauged the Zn one-form symmetry. And so this is the PSUN theory, as I explained before. Okay. So now, basically, we are understanding that the different global variants actually share the same TQFT in one dimension higher. And you can start looking for the classification of what are all the possible topological boundary conditions of this TQFT that we constructed with this procedure of making dynamical the background fields. For instance, this theory that I'm describing here, by like analyzing it carefully, you will discover that it has additional topological boundary condition, which you can write in this way: C plus RB equal to 0 on the boundary, with R going to 0 to n minus 1. And you can recognize indeed that this corresponds to the PSUN-R theory that I explained before. So this is something that you can try to do in general. You can construct this TQFT in the bulk, and you can start studying what are the possible topological boundary conditions of this TQFT. And for each of these topological boundary condition, you will get a slightly different theory on the boundary, which will have always like the same local dynamic, but different global structure. And this is very useful. And let me explain why. But first, let me mention how do we understand what are the topological boundary conditions of certain TQFTs. The reason why this method is much more like, let's say, user friendly, is that in TQFT, you can completely describe TQFT in terms of topological defects, with like fusions and braiding. Like you have defects, you can fuse them, and you have let's say a certain sum of other defects, general, and you have braiding relation as the one I described before. So you braid two defects, A and B, and you get certain phases. And so in general, you have a finite set of topological defects, and a boundary condition is in one-to-one correspondence with the maximal set of mutually commuting objects. Defects, let's say. Well, by commuting, I mean in the sense of braiding, of these braiding phases here. You want to have objects which, even if they link, you can unbraid them without picking any phases. And by maximal, I mean that once I fix this set, let me call it L. This is typically referred to a Lagrangian algebra. This is a set such that if you add to it another object, then any other object will be necessarily braiding non-trivially with those inside the algebra. So this is why it's called Lagrangian. It's like reminiscent of what you have in like symplectic geometry. And so the statement is that to any Lagrangian algebra, you can associate a certain boundary condition. And the way to do it is the following. Basically, you take your TQFT, and at some point, you put an interface between your TQFT and the same TQFT where you essentially gauge your Lagrangian algebra. So when you gauge your Lagrangian algebra, so this is made of topological defects, so are essentially symmetries of your TQFT. If you gauge it, this defect will become trivial. But then, since all the other defects break non-trivially with those inside the Lagrangian algebra, they are charged in a certain sense with respect to those inside L. So they are not gauge invariant, and you have to throw them out. So in the piece of your space where you gauge the Lagrangian algebra, the theory becomes trivial. And so this interface is not really an interface, but it's a boundary because it's an interface between your theory and the trivial theory. But then, once you define this boundary condition in this way, so this boundary condition is defined by prescribing that essentially all the objects inside the Lagrangian algebra can end on the boundary. Then, those which are not inside the Lagrangian algebra, so this is the boundary condition, those which are not inside the Lagrangian algebra will form the symmetry on the boundary. And on the boundary. And this is because essentially those which are not inside the Lagrangian algebra cannot end on the boundary. So if you put the defect and you push it at the boundary, it will not become trivial, and it will generate a symmetry on the boundary. So the symmetry that you get after you define a certain topological boundary condition is given by the bulk defects which are not inside the Lagrangian algebra defining your boundary condition. So you can describe what I told you in this case about SUN, PSUN, and PSNR precisely in this language, where the defects you are talking about are this Wilson surface of B, of B and C, this U and B. For instance, the boundary condition of B equal to 0 means that you are saying that the U can end on the boundary, and the V will, on the other hand, be stuck on the boundary, will live there, and it will be the topological operators. They will be the topological operators generating the one from symmetry on the boundary. And so depending on which boundary condition do you put, you have a different set of what are the topological operators, so a different global structure. So why is this language useful? Well, basically, each boundary condition is in one-to-one correspondence with some manipulation that you can do with the symmetry. So if you study the boundary condition and you discover that some of these boundary conditions are inconsistent, this means that a certain topological manipulation you would like to do is actually inconsistent. So this is the signal that your symmetry is an anomaly. In principle, you may think, okay, I want to gauge my symmetry, but if I discover that the boundary condition which would correspond to gauge the symmetry is inconsistent, then you discover an anomaly. How do you look for inconsistency of boundary condition? Well, as I told you, basically the TQFTs are characterized by this kind of braiding phases, and these braiding phases cannot be realized by boundary condition. So you can actually characterize in almost full generality what are the boundary conditions of TQFTs by studying what are the possible subset of topological defects of the bulk that can end on the boundary without realizing these braiding phases. And this is the way in which you can go on and do it for more complicated categorical symmetries. And I will just comment on this because okay, one point is the following. I introduced this tool in a way which seems like doable only for invertible symmetry, because I started by coupling my symmetry to background, and as I told you, this is something I cannot do for categorical symmetry. But the miracle thing is that sometimes, and I'm not saying sometimes, I would say almost, let's say always, we are discovering many cases in which this is possible. We are able to construct this higher dimensional TQFT for categorical symmetries, even if you are not able to couple the symmetry to background field. So this is like a miracle, and there are some good reasons why this is possible. And I can tell you, like, one reason comes really from actual holography. If you have a certain QFT with a certain categorical symmetry, and this QFT has an actual ADS-CFT dual, so it has a supergravity dual action. It turns out that if you look at your supergravity dual action, you just focus on the topological terms, like Chern-Simons-like terms, which are the most relevant when you look like very close to the boundary. This symmetry TFT is precisely identical to what you get by only keeping the topological terms of the supergravity action. So this is a way which you can get your symmetry TFT without being able to couple your field to background field. And this is something that has been done. And another method, which is kind of a trick, which is sometimes doable, is to construct this symmetry TFT by how can I say, by gauging in steps. Let me explain what I mean. One example of this categorical symmetry arises in 4D n equal to 4 super Young-Mills, which famously has a conformal manifold labeled by tau. And this theory has a very famous duality, which is called the Montagne-Olive duality. The SUN theory at coupling equal to tau is dual to the PSUN theory at coupling -1 over tau. So you see that tau equal to I is kind of special because tau and -1 over tau are the same, but still you are changing the gauge group. So this is not a symmetry. But since like 2 years ago, we know that these mistakes can be corrected at the price of making this symmetry non-invertible. So really, I really say categorical. So you have certain topological defects, which are three-dimensional defects, which form a certain categorical structure. I don't want to give you details about this. I just want to emphasize how the construction of the symmetry TFT works. So the first step that you can do is to say, okay, first of all, for sure, my n equal to 4 super Young-Mills theory will have a Zn1 from symmetry. So I can construct the symmetry TFT only by gauging the background for the one from symmetry. So this is what I wrote before this. But then one observation is that this theory, in 5 dimensions, since these are both two forms, has a certain zero form symmetry, which maps B and C to -C, B. This is a Z4 zero form symmetry. And you can try to gauge it. So the gauging process is a bit more complicated in this setup, but can be done, and you can study the TQFT arising from this gauging. So if I call this, let me use this notation. Let me call this Z of C naught, and let me call this symmetry. Okay, this is Z4. You can gauge Z4 zero form symmetry, and what you will get is the symmetry TFT for n equal to 4 super Young-Mills. Okay. And so you can try to study topological boundary condition of this TQFT. This is not that easy because it's a bit more hard than this simpler TQFT, but this is something that you can do. And by studying this topological boundary condition, surprisingly, you will discover that certain boundary conditions actually turned out to be inconsistent, and this proves that this categorical symmetry for certain values of n and other data turned out to be anomalous. And this implies constraint on any RG flow starting from n equal to 4 super Young-Mills, which is deformed by some relevant operator which preserves the symmetry. And this has been done, for instance, for a large class of RG flows starting from n equal to 4, like there are the so-called n equal to 1 star theories obtained by adding mass to the chiral multiplets of n equal to 4. This results in either gapped flow or gapless flow, and the structure of the infrared is strongly constrained by the presence of this symmetry when it is anomalous. And this can be studied with this tool. And I think that there will be many more results which will come in the next year by employing this tool, which is in a certain sense is really the generalization of coupling symmetries to background field. But you know, this is it looks a bit different, but at the end is what it is. So, okay, let me conclude here.
Okay, thanks a lot. Are there any questions from the audience?
If I can, I would do a simple one. Can you provide maybe some references and mostly the simpler ones, because maybe if somebody's not from the field.
Yes. Yes. Okay. Do you mean for the first or the second part?
I mean, both.
Both. Okay. For the first one, now I think that there are several lecture notes. I can tell you the reference, which are quite elementary. Oh, one nice thing is that this year
Can you
there
write?
was,
Can you write in the chat?
Yes.
Okay, so
Also last year there were 30 lectures about these topics. So there are also like video available online. I think that there is a course by Thomas Dumitrescu, which is kind of very pedagogical. This I would advise. And now I will write one lecture note, which I think is kind of pedagogical in the chat. Yes, this one. There are these notes by Laksha and students. I think this is the most pedagogical thing which is available now in the literature, because one of the difficulties that the original papers are quite hard to understand if you're not coming from the field. The language is very complicated. One thing, for instance, I try to emphasize this proof that in non-abelian gauge theory there is the center symmetry, which in the original paper it is incredibly mysterious why. And I met many people coming to me, ask me, but how can you prove that there are these topological operators? And indeed, this is not explained in the original paper. If you look in the internet, you can find some talks in which somebody explained this in this way, but it's never totally clear. So yeah,
okay.
As I told you, the language seems a bit different from what people are usually used. I think that these lecture notes are kind of pedagogical.
Okay, thank you very much for these notes. Maybe if you had anything else in mind, you can write that in the chat or also tell us later. And so this is triggering another question. Obviously, I'm not from the field, but as I listened to you, I got that this is a field which is evolving recently, if you want, which is not that, I mean, there are other fields in physics that are not getting this kind of novelty in these years. And so I would like to make a more general question. I would like to ask you, in your opinion, what are the perspectives? How will this thing evolve? And how are you communicating with mathematicians? And how much is the communication problem affecting the field itself? And is it one of those examples that we are taught at some point at university in which we say, physicists gave an inspiration to mathematicians to do things?
Sure. Okay. Thank you very much for this question. First of all, I want to say that there are two fruitful contamination. One is with mathematician. It was like really at the beginning, because we were using a lot. At the beginning, we were using a lot of tool of category theory, and still we are trying to using it. But as I try to emphasize, it could be, I mean, more physics friendly to try to avoid it. But another contamination which is becoming very fruitful, and I believe that this is really what will happen the most in the future, is discussion with condensed matter physicists. There are many of the symmetries has a lot of application in condensed matter, and there are many ideas from condensed matter that we're bringing. So this is like a discussion which is going in both sense. And as you suggested, the discussion is not always easy, because people from different fields typically speak different languages. So maybe there are things that we call in some way, and they are calling in a different way, but there are the same things, and it takes some time to realize it. And same thing with math. And also, I feel that the discussion with mathematicians is a bit more hard than with content matter physicists, because they are mathematicians. Content matter physicists, at least are physicists. So with mathematicians, the problem is that they are really interested in different topics. I mean, sorry, not in different topics, but they have different motivations. So sometimes they are studying the same problem, but with a completely different motivation. So their paper are sometimes their main goal is completely irrelevant for us, or vice versa. So they are maybe studying in great detail certain symmetry structures, which for us plays no role. For instance, let me mention this, that I haven't discussed this in any detail, but there are different kind of categorical symmetries, and one like very rough categorization is that there are intrinsically non-invertible symmetries and non-intrinsically non-invertible symmetries. A non-intrinsic non-invertible symmetry is some symmetry which can be obtained from some invertible symmetry with some mixed anomaly or something by gauging a symmetry. So sometimes you can induce a non-invertible symmetry by gauging something, but something discrete. So this is a kind of manipulation which commutes with the renormalization group flow, and therefore, if you want to use this symmetry to predict something about the infrared, it's kind of useless, because you can say, okay, my theory in the ultraviolet has this symmetry, but then there is no reason why I have to predict the infrared by studying the symmetry. I just can go back to the theory with just invertible symmetry that I know very well how to analyze, predicting the RG flow, and then gauging the symmetry at the end. On the other hand, intrinsically non-invertible symmetries are much more interesting for us. As you can imagine, these are the symmetries which cannot be obtained by invertible symmetry by gauging. And so there are, for instance, a lot of papers in mathematics which are studying in a very complicated way the structure of symmetry, which for us are non-intrinsic non-invertible symmetry. So if you want to say something about the dynamics of QFT, we don't really care much about it. And so there are, maybe you have to be able to recognize what is relevant, what is not. But at some point we are trying to make this discussion fruitful. There are many conferences in which there are both physicists and mathematicians. So at some point we are trying to unify the language. I think this is very fruitful also for them, because sometimes even if we are not rigorous, we arrive at some result in a quick way. So we offer to them something to prove, so they are happy. But yeah, okay. So this is with condensed matter physicists, the discussion is a bit more easy, even if sometimes they describe the system in a very different way. Because, for instance, the low energy physics sometimes is the same, but they describe the ultraviolet not with a continuum quantum field theory, but with a lattice model. And so now it is becoming very popular, and I think that in the coming years this will be one of the main subjects which will enter from condensed matter to high energy physics, to understand better high energy physics, the topic of realizing symmetry on the lattice. So you can realize some quantum field theory as the low energy of a lattice model. And it turns out that symmetries that on the continuum are very easy to understand, on the lattice are much more complicated. And so now there is this field which is emerging, and I think it's very interesting. It will have a lot of future.
Wow, thank you.
So I guess we can thank again our speaker.
Thank you
for this interesting lecture, and we will see again with another theory lecture by young researcher on the 20th of December. And with this, I close this session. And thanks again, Andrea, for your lecture.
Thank you. Thank you.
Bye.